This is Paradise Podcast number 68, and today we're talking about the aerodynamics of flying animals. So in podcast number 6, we had a similar topic. It was aerodynamics of birds, but this one we're not only looking at birds, but just flying animals in general. If you haven't checked out podcast number 6, check that out because there are some really juicy tidbits in that. But in this podcast, we're going to be looking at a paper called The Flight of Birds and Other Animals. And it's quite a juicy topic, and we'll maybe make this 2 podcasts, I'm not sure. Let's get into it. So they say, in light of engineering, we begin to see that what can be done and start to look in detail at how birds do things that we did not really expect, like leaving Alaska and spending a week flying nonstop to New Zealand, or using natural thermal convection to fly from Europe to Africa and back for no cost at all. So, for example, in podcast number 6, we're just talking about the flight mechanics. Now we're talking about their general patterns of flight. So they can fly from Alaska to New Zealand, which is like 10,000 miles, or from Europe to Africa, which, depending where you are, could only be like a few hundred Ks or even not even that, or back, but I don't know, but for no cost at all, because they take advantage of natural thermal convections. And they say that animals have been flying for 200 million years, and birds are not the first to succeed or the only ones to try. However, they've built a wind tunnel or they've initially built wind tunnels back in the 60s on how to test birds, and then from there they've developed them. So let's look at animals in wind tunnels, how to test a flying animal in a wind tunnel. So they say wind tunnel engineers are used to working with models of reduced size, flown in conditions that are not the same as in the real world. Those problems are not the case for testing birds, though, because if you select a bird like a pigeon, you can fit the entire thing in the test section and set the conditions as if they are outdoors. So that's a very nice thing to not have to worry about. In almost all engineering, in almost all aerodynamics, you look at reduced similarities. So you have to maintain Reynolds number similarity, for example, and a smaller wind tunnel, which means you have to increase the velocity usually. And often that doesn't work out too well because often you can't get the same Reynolds number. But for birds, it's very easy to do. So that's quite nice. They say that the pigeon does not have any anatomy in the way that an engineer can understand. Okay, that's a little bit out of the box, I'd say, but they say if you hold a pigeon in the hand, its wings are folded up, and if you unfold them, they can be set at dihedral angles from minus 60 degrees to 90 degrees. Well, that's not something that an engineer can't understand. We do understand degrees, so there. Anyway, and the span of the wing can be anywhere from 1/3 to the whole outstretched span, with all these kinds of angles that can be set by muscles at a wide range of values. So in podcast number 6, I talk about this a little bit more as well. Let's continue. So a pigeon wing cannot be set by hand into a position that is meaningful for flight. So that means that really, when a pigeon flies, it's so complex that they have all these different mechanisms to change the angle of the different parts of their wing. So not only the entire wing, but the first half of the wing compared to the second half, the rotation of the feathers, and even the wingtips and everything. So trying to put that in a wind tunnel and set it manually, it doesn't really work. You need to have the pigeon do it itself because it knows what it's doing. On the other hand, the whole pigeon can be trained to fly in a wind tunnel, and it will set itself into posture for whatever kind of flight it has to perform. So in reality, they say you do not measure forces in a bird in a wind tunnel. You let the bird set itself up and infer the forces from the geometry from its situation. So that's only partly true. You can do that way, but you can also a way which is not very nice. You actually have to perform surgery on the bird and actually install strain gauges and that in its body, so you can see what forces are where. As I said, this way that they're talking about is much better, where you just put it into the wind tunnel and you look at how it situates itself in the wind tunnel with different velocities, and it's much nicer for the bird. So bird wind tunnels are designed to achieve given levels of performance without being too expensive. Engineers, when consulted about this, often say that the best way is an open circuit suction tunnel. So what that means is you have upstream the test section, and then downstream you have this fan which sucks all the flow out. And they say, however, this type of design works very well when used in the wind tunnel laboratory, where the test section is carefully sealed. However, the ornithologist cannot leave this bird unattended. He needs to access it, and consequently leaves holes and doors open, which allows outside air to rush in invisibly and disturb the flow in the test section. So a suction tunnel ultimately doesn't really work for birds because if air can get into the test section by routes not noticed in the design, it means that you can't really have a closed system which you can then analyze the forces on the bird the way they want to. So in practice, blowers and recirculating tunnels can be used, but suction tunnels are not practical for any form of quantitative work on live birds. So a blower tunnel is similar to a suction tunnel in that it's just like a long tube, but instead of having the fan downstream sucking the air, you actually have the fan upstream pushing the air down. And then recirculating tunnels are exactly what they sound like. They're just closed loops. So the air goes through the test section, then goes around in a loop and continually goes around. There are benefits and detriments to each type of these wind tunnels. I go through them in quite a few podcasts, so I won't go through them here. But they have a picture of one really cool wind tunnel. So they have a hydraulic powered wind tunnel at Bristol. They made in 1966, and they moved to Nairobi in 1970. And they said that this tunnel was powered by a ventilating fan with a contraction ratio of about 4. So there's a fixed theta vanes before and after the fan to straighten the flow. And then there was a honeycomb and fine mesh before the contraction. And then they have effectively the end of the contraction, and then that leads to an open test section. And then they put the bird in this part. So the bird isn't actually inside any wind tunnel. It's like situated just downstream of a fan effectively. And this thing was quite big. It was about 4 meters in length and about almost 4 meters in diameter as well. So that was one of the first, if not the first, wind tunnels. And it could achieve a maximum speed of 22.1 meters per second. So that's quite fast. They say a better solution was built by some company in Sweden and installed in the biology department of Lund University in 1994. And this is a closed circle wind tunnel with a test section measuring 1.2 meters across and 1.08 meters vertically. And the contraction ratio was 12.25 to 1, which is very high. That means you'll likely get a very good quality flow. And interestingly, it was rigged so that the entire wind tunnel, can be tilted from an 8-degree descent to a 6-degree climb. So let's have a look at this wind tunnel. So it's a closed loop wind tunnel, and the entire thing is effectively installed on a seesaw. And at one end, you have a rack and pinion gear, which means that you can, just by rotating the gearing, you can elevate one side, which then it tilts the entire wind tunnel up or down. So that's really amazing. So that means that you can mimic a bird at different conditions because the gravity forces at different angles as well, effectively. So they say that the experimenter can move the equipment in and out of the gap in the test section or reward the bird for its performance without disturbing the flow where the bird is. So they have a opening behind the bird in the test section, and if the bird does well, the researcher can give it some food as a reward. And they say that another version of this wind tunnel was installed by the same Swedish manufacturers later at the Max Planck Institute at Seewiesen in Germany. But this one has a horizontal circulation and omits some of the original features, notably the tilting facility. I'm not sure how beneficial having a tilting entire wind tunnel would be, but it's nice to have, just so you have. So in terms of gliding flight, they say the simplest way to use a bird to make its own movements, so to make its own measurements, is to train it to hold a constant position in a wind tunnel, in which the airflow has been set by the experimenter. For example, just about any bird can be trained to fly in a wind tunnel in a body of air that is moving slightly upward relative to the horizontal, at a speed that is within its normal range. By doing this over a range of speeds and finding the minimum descent angle at which a bird can fly without flapping its wings, basic glide polar can be found for this bird. So you don't have to worry about small amounts of drag caused by poor wing. This is interesting. So they say you don't have to worry about small amounts of drag caused by poor wing-to-body junctions because all birds are constantly modified by natural selection to deal with small performance defects caused by minor variations of anatomy. So that's, I don't know about you, but I find that really interesting that even minor changes that might make the bird 1% less efficient at what it's doing or effective, over time, natural selection will breed that out and it won't be a problem anymore, even just a small variation. So that's, if you've ever worked with genetic algorithms, you'll know what I'm talking about here, and it's really quite amazing how this happens. So for birds, you don't have to worry about defects, which is quite nice. And they have a pigeon in the Bristol wind tunnel that we mentioned earlier, which was just the simple blow down is effectively just a fan, and the bird goes at the back of it at different configurations. And depending on how the bird's wings are displayed, the lift coefficient ranged from 1.3 to 0.3. So when the bird was entirely outstretched, so this is a pigeon it looks like, the lift coefficient was 1.3. And then when it sort of brings its wings in a little bit, so probably about 3/4 extension, then the lift coefficient dropped. And then when it went to very compact, it was 0.3. And the platform that it adopts depends on the speed that it wants to glide at. So if it was going very fast, you don't actually need to have a very high lift coefficient because you can produce as much lift as you need to maintain glide without outstretching your wings too much. The benefit of that is that you can drop the drag, which means you can glide further. So when they tuck their wings in very close to their body, that's usually when they're going very fast, and that means that they don't need to have as much lift being produced. So the pigeon's wings can move about the shoulder joints, forwards or backwards, up or down, and twist nose down or nose up. And not only that, actually different parts of the wing can do it independently as well. As I mentioned in podcast number 6, I go through these mechanics quite a lot. So they say to control speed, the bird moves their wings forwards or backwards like a hang glider pilot. Moving the wings forward also spreads them to the greatest area, while moving them backwards allows the elbow and wrist joints to flex so that the feathers of the wings slide inwards over one another, reducing the span and area of the wing. So I'm guessing that when it does that as well, it probably makes its own wing a bit thicker, because if you have all the feathers clumping up, they're naturally going to have to take up a greater thickness because then it can't be spread out in the other two directions as much. That's what I think. Anyway, so moving the wings forwards also spreads them to the greatest area, as I mentioned. So fast gliding birds can reduce their wing area and span to less than half the maximum values without losing any strength whatsoever. In fact, I think that probably that also increase strength, because if you have all these feathers very close to each other, they don't have as much of a relative bending moment between each one, which will probably make them a little bit stronger overall, I think. So this is possible, this grouping them together. It's possible because the birdwing is a multi-spar design, with the shaft of each feather being a local spar for its own part of the wing. So a spar is a familiar term that we use for aviation, and that usually indicates just the central beam that runs in a wing. And often wings have 2 spars, and the big ones sometimes can have more, but they are the main load-bearing structures of a wing. Then you have ribs, and stringers and that, but the spars are the main features. And here, each wing effectively has its own spar. Each feather has its own spar for a plane, for a bird. Sorry. The same movement that adjusts the area of the wing also serves to control the area by allowing the feathers to slide over one another. Varying the span is a better method of adjusting wing platform for speed than adjusting the chord, for instance, by foul flaps. So compared to our way of, we can potentially adjust for speed. We, like people in general, we've designed these things called foul flaps, and they are just the flaps that you find at the back of wings. So what that does is you can adjust the chord and also the camber effectively of the wing. And instead of doing this, birds just adjust their wing platform's size, so the span of it. And we don't really do that for aircraft. Our method is different, and apparently birds, their method is better, which I'm not too surprised at, because they don't have a much more complex design. So how do you measure drag of flying animals? So they say to generalize a measured glide polar, that is, adapt a measured polar to get new polars for other birds, you can add up sources of drag starting with the drag of the feathered body minus wings. If you try that though, you'll get into trouble straight away. So that's the sound of the other shoe falling. You can't do it that way. So if you take a dead bird or a stuffed one or a simulated one, no matter what you do, the airflow just separates from the body's surface and will not reattach. I'm guessing that they're talking about from experience. So this method gives a drag coefficient of 0.3 or more, or even more, like a football. As with all wind tunnel measurements on birds, trying to measure drag on parts of a dismembered bird is useless, and I would not suggest that you try. So it was noticed some years ago that this body drag coefficient is one of the two morphological variables needed to calculate the speed at which a particular bird requires minimum power to fly level. The other one is the dimensionless variable k, which accounts for differences in lift distributions from the idealized elliptical distribution. So let me talk about this briefly because it's a very in-depth topic. So the idealized elliptical lift distribution, what is that? So in a nutshell, it's an elliptical distribution over a wing platform. And the reason why it's called idealized is because it really stems from like the history of aeronautical engineering, where back in even the 1930s, a lot of some really smart aerodynamicists figured out that the most efficient way of producing lift on a platform is by having an elliptical distribution of lift. And the reason why that is because it dramatically, or actually reduces the induced drag to zero if you get it right. And why that is, if you think about it, is that if you go, the elliptical distribution means that when you get closer to the wing tips, the lift drops. So that means that when you get to the wing tip, ideally you should have no lift being produced. And what that means is that there's no pressure difference between the bottom and the top surface. And if there's no pressure distribution difference, then there's no bleeding of air from one side to the other, and no wingtip vortices. That means that there's no induced drag. Now, trying to get an elliptical distribution is quite difficult in practice because you can have an elliptical planform, and if you just have the planform itself, you will get that. But a platform itself is not really beneficial for flying because you need other parts of an object to fly. You need a fuselage, for example. You need perhaps a tail. You need a power plant, and all these different components affect the aerodynamics of the elliptical wing because you have different accelerations and decelerations of flow around it. So an elliptical wing on an airplane will not actually produce an elliptical lift distribution. You actually need to change it a little bit. So that is the elliptical distribution in a nutshell and why it's called ideal. It's usually the best thing that we can aim for in terms of reducing the induced drag and making the wing as efficient as possible. So coming back to this paper, the dimensionless variable k can be got from field observations of wild birds and is a little below 1. So this is because of splayed feathers at the wingtips. So this is directly related to the idealized lips. So 1 being perfect and below 1 being not perfect, but it's pretty close to 1. So the other variables for the calculation are easily measured. So for the drag coefficient, like the wingspan, gravity, air density, and so on. The experiment for the body drag coefficient is to fly the bird level and measure its wing beat frequency, where it is easy to show that the small variations of frequency vary directly with the power. If the drag coefficient is high, the minimum power required to fly level comes down. If it is low, the drag coefficient, then that goes up the velocity. So you take a few dozen of those frequency curves from the minimum to the maximum speeds at which the bird will fly horizontally, and having measured the minimum power to fly level velocity, you turn the equation around to get the body drag, so the drag coefficient. So instead of actually sticking a bird on like a load cell or something, you can infer it from how much it flies, beats its wings at what velocity. That's a cool little trick. So the power in biology. So a bird flying horizontally overcomes drag by flapping its wings about the shoulder joint. The flapping motion results in a mean horizontal thrust force, and this force multiplied by the speed is the power acquired from the flight muscles. So birds are very cool in that their wings have to do everything. They have to not only produce the lift, but also the thrust. Whereas for our airplanes, for example, fixed-wing airplanes, we have the wings doing just the lift, and we have the power plant, so the turbojet or the turbofan or whatever, doing just the thrust. Whereas the wings for birds, they have to do everything. That's why they are so complex. And they're also more efficient as well, so there's that. So to measure the drag, you have to measure the rates of all processes in that living bird that require energy from fuel reserves. This begins with the basal metabolism, the power needed to keep the bird alive, which roughly scales with about 0.75 power of the body mass in birds. So in other words, as you increase the mass of the bird, the relative amount of power it needs out of its entire power that it uses drops because it scales to the 0.75 power. So the mechanical power to fly, and neglecting comparisons, varies with about 1.17 power of the mass of the bird. An African vulture, for example, requires less than 4% of its cruising power to stay alive, whereas a small passerine like a goldcrest uses over 30% of its power for the same purpose. So one interesting fact that I came across years ago was that birds about the size of a pigeon need about half its body weight in food each day just to stay alive. That's how much energy it requires to fly and do what it needs to do. Flying requires a lot of power. And that's one reason why humans can't really fly. As a general rule of thumb, a typical human can produce about 5 to 10% of the power required to fly. So that's what we're nowhere near close to flight. Whereas birds can produce all the power that it needs, which is why it needs more food. So the small bird also goes slower than the larger one. Consequently, small birds cannot afford any kind of migration strategy that wastes time, whereas large birds can use soaring procedures that cut their energy expenditure at the expense of a lot of time spent soaring at thermals. The reason why is because it doesn't use as much power to stay alive, whereas small birds use a lot more power just to stay alive. So it needs to get to where it's going quicker, and it can't dilly-dally around with these nice cruising soaring procedures with thermals and blah, blah, blah. So they have to adopt different flight patterns, as we'll get into as well a bit more later. So biologists know that using muscles to generate mechanical power results in the consumption of fuel, but they call this metabolism. And think of it as something that occurs during muscular activity, but not connected with any other changes that occur in flight. They never measure the air density or think about gravity changes. So that's one also bone that I have to pick as well, where they don't measure air density changes. Neither do most aerodynamicists. In fact, a lot of them just ignore it, even though it does change in their experiments. So actually, I should probably plug an instrument that we do here. So we make an instrument called the Atmosphere Hawk. It actually measures the density of air in your experiments. And the reason why this is important is because on a regular day, the density of air changes by about 2 to 4%. That's just a regular day. And those errors will be in your experiments, and they also affect any of your validation with your CFD. To look at these errors, just not only in the flow physics, but also the forces, look at podcast number 54, where I go in detail about how this happens. So make sure to get an Atmosphere Hawk to measure the density of air so you get that error out of your experiments and make life easier for yourself. Link in the description. So let's move on. So if the bird is flying, that is enough, and if it does maneuvers like cyclical acceleration and deceleration, they are typically just ignored. Consequently, published measurements of the rate of fuel consumption when flying, which have been made by physiological methods, are not very helpful to the flight theorists because they miss out on all these different maneuvers. They don't categorize them properly. So the key to using this approach for practical calculations is to define a speed at which the bird requires less power to fly than one flying faster or slower, and devise a practical way to measure it. That could be done by measuring wing beat frequency in level flight, as we mentioned earlier. By putting the bird in the wind tunnel, you measure how many times it beats its wings, and then from there you can calculate the drag coefficient and other properties. So if we extend our known measurements upwards to birds bigger than any we know, so 20 kilograms and above, we find that the wing beat frequency goes down, and the work done by each gram of muscle in each contraction goes up until eventually the bird cannot fly at all. So this is why you don't get birds above 20 kilograms flying. So the requirements for stress and strain are above the limit for flight muscles for these birds. There are no huge flapping birds. Beyond a certain size, there is no room for extra muscle to fly. So the bird cannot lift extra load in the form of fuel or do subtle maneuvers to change speed or avoid obstacles. Current birds fly up to a body mass of around 16 kilograms, but they have obvious difficulties, and there are none above 20 kilograms at all. So what they're saying here is, once you start getting bigger, you not only struggle in flying, but you can't even take any payloads. So if a bird wants to munch on something beforehand and then try to take off, then it can't even do that because that little bit of extra weight is too much for it to handle, because it's just the requirements for flight are too taxing on its muscles that its muscles can't produce enough power. So that's also another reason probably why humans can't get there either when we're anywhere between 60 and 150 kilograms. That's far more than 20 kilograms if my math is correct. And that is not good for our muscles to be able to produce enough lift. So maybe a child could maybe fly. I don't know, like a 3-year-old might be able to fly. Anyway, don't try it. Anyway, there was once a group of very large flapping animals, the last known pterosaurs of the Cretaceous period. At the end, for a short time, they had a wingspan approaching 12 meters, far more than earlier pterosaurs. We don't know what happened, but most probably the Earth changed by changing materials in the mantle in a less dense form, moving them outwards. This would reduce the surface gravity without changing the Earth's mass. So that's interesting. I've never thought about this before, how changing the composition or changing the arrangement of the mass of the Earth would affect how well things can fly. I'm not sure if this is true or whether there are other things to do with their physiology that modern birds don't have, but it's interesting to think about. So if we extend the measurements down to miniature hummingbirds, 3 grams or less, the wing beat frequency gets so high that the wing muscles do not have time to get ready for the next contraction. A problem that insects overcome with a different type of muscle that develops low amplitude contractions in the kilohertz range. So in other words, they have a different set of muscles that don't extend or contract nearly as much, but they can do it quicker, so they get the kilohertz range in terms of their frequency. So meanwhile, the regular sized birds all have essentially the same anatomy with adjustable mass, wingspan, and wing area. They obey the rules and adjust everything together. The best combination of power and wing beat frequency is found in medium-sized birds, especially waders of around 300 grams, some of which fly over 10,000 kilometers non-stop. That's insane. So humpback whales migrate about 10,000 kilometers as well in their journey, but they're in water swimming around. They'd have to work nearly as hard as 10,000 kilometers flying. So the range performance fades into nothing for very small and very big birds. So the accuracy of calculations. Let's talk about this briefly. So the flight program, which is a program that this author developed for the BBC actually, prints out a list of current values of 30 variables that change as the bird goes along, starting with the mass, the speed, and the power. So the Lund wind tunnel that we talked about back in 1966 was originally designed to make checking these different values possible during a long flight in the wind tunnel. So this is interesting. To do that, you have to swing a balance into the test section every hour or so and stop the wind tunnel for a minute or two so that the bird can weigh itself. So the bird steps onto a scale and weighs itself, which for some reason I find endlessly humorous. So the migration of small birds. So small birds have much the same density as big ones, and scaling effects to see it that their speeds for minimum power and maximum range can be calculated like big birds. The winds are the same for any bird, and a goose that can cruise at 20 meters per second does a lot better than a sparrow going at 10 meters per second for the same winds. Another general effect of scaling laws is that big birds have higher aspect ratios like 9 for a goose, whereas little birds that flit around in the bushes typically have aspect ratios of 5 to 7. So what this means is that a bigger bird is typically going to have a more efficient flight as well, because a greater planform typically couples with a reduced induced drag, and that's better for the lift to drag ratio, which means that they can glide better. So along with this reduction in aspect ratio for the small birds, that means that if you think of the migration range in terms of energy height, so the energy height is like if you take a bird and you try to see how far it can fly up, that's at the energy height before it runs out of energy. The distance that each bird goes depends on the remaining energy height and its lift to drag ratio. This is called Breguet's law, and this is a law, an equation, Breguet's range equation, that we also use in aviation, which just tells you how far you can go based on these parameters, like your lift to drag ratio and how much fuel you got left. It's also affectionately known as the Breguet's law because it's more tasty that way. Anyway, small birds in general have smaller lift to drag ratios than larger ones, as I mentioned earlier, and waste more energy than on their basal metabolism, as we also covered a bit earlier. So small birds have to get to where they're going quicker so that they don't waste as much energy and they can feed again without uh, expending all their reserves. So low cruising speed is a major time waster and waster of energy for small birds, as they use energy for their metabolism to stay alive. And the smaller the bird, the bigger the fraction of that total power is needed. They need to do something that allows them to increase their cruising speed, which will save on basal metabolism without a big penalty in the lift-to-drag ratio. So scaling laws also show that swans can hardly find enough power to fly, whereas blackbirds, whose muscles shorten at high frequencies, so as we mentioned earlier, the blackbirds, because they're small, they beat their wings at a higher frequency, and their muscles can't contract and expand fast enough because they're going so quickly, they're beating so quickly. So what they do is they limit how much they can contract, so they can beat quicker. So these blackbirds have plenty of power for takeoff, sudden changes of direction, and so on. So does a blackbird cruise along using only half of its flight muscle? No. Rather than that, it uses the whole muscle at a higher frequency, but only for part of the time. So the characteristic flight of small birds is called bounding. And this type of flying, bounding, is where the bird flaps for a few wing beats, then closes its wings completely and follows a parabolic flight path with the wings closed for a short time. So what that means is it flaps its wings, it gets a lot of power up, a lot of speeds, and it shoots up a little bit. Then it stops beating and it brings its wings close to its body and it allows itself to fall back down to earth while it's still traveling forward. And it does it again. It beats its wings and keeps going like that. So it goes in this parabolic path. So if you work, as it needs the same mean power as before for a shorter flapping time, the work done by each gram of muscle while flapping also goes up. The muscles work more efficiently at higher power. If you work out the minimum velocity, the velocity for minimum power cruise and the maximum range velocity for a bird that is bounding, the bird works at full power as it pulls up while flapping, which brings the muscles into the most efficient operating range. The acceleration that a small bird can pull while flapping is about 4 Gs. That's really fast, 40 meters per second, meaning that it can maintain a power ratio down to 0.25. So that means that only 25% of the time it's flapping. The other 75% of the time it's not actually flapping. It's not doing anything. So in a quarter of the time it's working while it's flying effectively. The other 75% of the time it's falling with style. So this may push its maximum range speed up by 11% or more. Bounding is a peculiar habit of birds and seen only in smaller species that are specialized to fly in this way. So let's talk about the energy height for planes and birds, as we touched upon earlier. So the energy height is the height that a bird would get to if all of its stored fuel were converted into height using the engine, the muscles that it has, as I talked about earlier. All birds with the same fat fraction and the same physiology come out at the same energy height, which is a logarithmic function of the fat function. Theory says that the range is just the energy height multiplied by the lift-to-drag ratio. So that's very nice. It comes out very easy to calculate. And then they have a graph here showing the energy height of a bunch of different birds while they're migrating. So these birds migrated over an air distance of over 3,000 kilometers, which is pretty far, I guess. I've seen further. Anyway, the energy height. So a lot of these birds, for example, the geese, they start at 640 kilometers. So if they were to just fly directly up, they could get to 640 Ks without consuming anything before they expire. But these geese, over their flight path, they drop in weight because they're using all this fat for energy. And when they get to about 2,800 kilometers, some of the geese land, feed to get their energy height back up, and then they finish off their path. Others didn't, so I'm guessing those ones that didn't had enough energy to begin with to make it, or at least they thought that they did. Now, other birds, they started at about 400 kilometers, their energy height, and then when they got down to about 200 kilometers, in theory, they all pretty much stopped, fed, and then continued the path, so they wouldn't drop below that 200 kilometer barrier. They say bird flight ranges are a little more complicated than those of aircraft, as all birds, as they think, have a dual fuel system in which the main energy supply source is fat. This is the best long-range fuel because it can be stored in a non-hydrated form, which makes its energy density 3.9 megajoules per kilogram, which is much higher than for any other form of animal fuel. However, animals also get usable energy by burning carbohydrates or protein. And a migrating bird, once it has been going for a few hours, no longer needs the amount of flight muscle that it needs to get airborne at the start. That muscle becomes progressively surplus to requirements, so the bird burns it. Birds get most of the way by burning fat and a lot further by burning their engines. That's pretty amazing. So they're losing their gains there. That's not that good. So these, certain birds called godwins, they migrate from Alaska to New Zealand, as we mentioned, with a fat fraction starting at 0.55. And they actually have enough fuel left to carry on to the South Pole if they really wanted to do that. So they can fly almost from the North Pole to the South Pole without having to really feed. But at the start, they are 55% fat. So that's the end of this podcast. I reckon I'll stop it here and make the second podcast for the rest of what we have covered, which will be about feathered birds and bats and pterosaurs. So make sure to check that out. That'll be coming out in a few days' time. And also in the meantime, make sure to check out the atmosphere hawk, which I mentioned earlier. It's not actually a bird, it's an instrument. We call it the hawk though. But it measures the density of air very accurately so that you can take the air out of your experiments. Link in the description. Make sure to like, subscribe this, and see you next podcast. Peace out, amigos.